Hey, what's going on, everybody? You know who it is. It's your boy, Algebra, coming to you live and direct from the studio. I just want to say shout out to my homeboy, Averick. He's sleeping tonight. Hopefully, he doesn't wake me up at 12:30 in the morning and keep me up until 3 like yesterday. That's the price we pay for greatness, though. Having said all that, let's do some derivatives, and we're not talking about polynomials anymore. The main thing that you guys need to understand is so far you've only been using two things: the power rule and the chain rule. Those two are foundational pieces of all the things that you can do with a derivative. The power rule said that if you had ax to the n, it would become na x to the n minus 1. And let's take the power down to the front, multiply it as a coefficient, and then drop the power down by 1. The chain rule said that if you had something on the inside, you needed to also deal with that derivative. So instead of looking at just a times x to the n, now this part would say something like u to the nth power, which meant that when we do the derivative, all of that stuff from the first part stayed the same, but now we also need to use a du dx, which was the inside derivative. This was for problems that had extra parentheses in it. Anytime that you saw a parentheses, it automatically meant that you had to use the chain rule. So that's not going away, neither is the power rule. But now I need to actually introduce you to some of the other derivative concepts that are going to come into play this chapter. This is actually a much larger chapter than we've used up to date. Everything that we've done, like I said, has been connected to either the power or the chain rule directly, and no other possibilities existed. There hasn't been any trig. There haven't been any exponentials. But those are the two major ways that you need to understand derivatives as a concept, as instead of just looking at the things we can do with polynomials. Having said that, let's go ahead and talk about our first one. Let's talk about exponentials. We're going to be talking about y equals e to the x. In the basic idea for y equals e to the x is that if we wanted to, we could set up the same difference quotient as we originally had. The limit as h approaches 0 using f of x plus h minus f of x. All of that was over the top of h. And what that said is basically your slope formula, but it was the definition of a derivative. And for this problem, y equals e to the x, we're going to go ahead and substitute some information in. The limit's not changing, but instead of saying f of x plus h, what you guys should understand is that we're using e to the x plus h. This one is just going to be e to the x. The h on the bottom is going to stay the same. Now, my thought process says that at this point I can do some magic of exponent rules to break this thing apart right here. I don't like the way that that looks. It's too much. It's too complicated. But if you think back to when you were in Algebra 1, you learned the rules of exponents, the product rule of exponents that said if you have two exponents and they're added together, that automatically means that it was a multiplication problem to begin with. I can change this thing into being e to the x times e to the h on the top, which now I can factor out. And here, there's some magic happening. It was not one of the things that we talked about during our study earlier this year, but e to the h minus 1 all over h is a limit concept that reduces down to 1. This entire thing is actually just going to disappear. It's gone. The fact that that limit is disappearing is actually really convenient because all you're left with is just an e to the x. If I give you y equals e to the x, then the derivative dy dx is also e to the x. And that's a pretty good situation for you to have. This is your first rule. The first new rule for today, it is the rule of exponentials. And unfortunately, it does not apply to problems like 2 to the x or 7 to the x. E is special. E is is a conceptual number that came up so much in math that they just had to go ahead and call it out for what it is. We're only going to be using E. So let me show you a small variation to this exponential rule. I can include a chain rule problem in it, such as this. If I give you the problem y equals e to the 7x squared, this says not only do you have an e to the x problem, but you also have a chain rule problem right here on the inside. The dy dx for this particular problem, when I bring down the power from the 7x squared, I would get 14x. All I have to do is multiply that times the derivative of the whole thing. Done. This part represents my chain rule, and the e to the 7x squared is just what I got from the original exponential rule. So it's actually not that hard of a thing to do using e to the x. Let's try one more. Y equals e to the 5x plus 11x to the third. And all of that is an exponent. Conceptually, what we've just talked about, this new rule of exponential says you're automatically going to have that same thing. It's not going to change. But the chain rule part says you also need to do the derivative of just the top, which is 5 plus 33x squared. And keep it in parentheses. I don't need you to simplify that. You're done. There's no need to try to do anything extra in this particular problem. So again, the new rule is the rule of exponentials. E to the x becomes e to the x. But you still have a chain rule. Let's talk about another rule then. Another rule that you need to understand is y equals ln of x. Ln and e's go together. This is like log base e. And we're going to keep it just to talking about e's this time. This one's straightforward, it's simple. Y equals ln of x becomes dy dx equals 1 over x. This is the natural log rule. And that's it. That's the whole thing. That same type of magic dealing with the actual difference quotient is going to reduce it all the way down such that y equals ln of x. The instant rate of change from that, the slope of any tangent line, can be found by just plugging in 1 over x. Let me show you the picture for this. Ln of x looks like this as a graph. And so what we're saying is that the slope at any one of these points along the way can be found by just doing 1 over x. Pretty powerful thing. So let's go ahead and make it a little bit more complicated. What can I make this thing look like? Well, I could do something like y equals the ln of 5x squared. That's going to become 1 over 5x squared times 10x. And again, this 10x comes from your chain rule. That is the derivative of just the inside. But obviously, this time you can go one step further, or maybe two. There's our final answer this time. So what you're looking at in this particular situation is when we're talking about ln's, you may have more steps to go. You may have to go and simplify something, but the basic idea is there. The ln becomes 1 over x. Let me talk to you about y equals ln of 3x plus e to the 7x. Just like the power rule, if you have two different terms, treat them separately. Just do it. The first one is our newest rule, the natural log rule, which says it becomes 1 over 3x times 3 plus 7 e to the 7x. That's that exponential rule. Yes, you still have to go ahead and do your simplification, but this is what you end up with. 1 over x plus 7 e to the x. Done. I apologize for having so many different things pop up on the screen just a second ago. I need to figure out how much time I had left in this video, and it wasn't showing up for me. So let's keep on going. Got about 3 minutes left, and I've got 3 different trig functions to talk about. I don't know if I'm going to be able to finish, but we might as well try. 3 trig functions that you're going to have to deal with. Y equals the sine of x. Y equals the cosine of x. And then y equals the tangent of x. Not going to worry about trying to give you guys those others. Not going to worry about having the cosecant, the secant, or the cotangent involved in our particular investigation of trigonometric derivatives. So for this one, I want to talk about y equals sine of x. And I want to talk about the graph that you learned a long time ago. This is a wave. The wave itself is nothing special. We know how to deal with that. But I want to draw your attention to a couple of points. Like right here. There's a tangent line. Here's a tangent line. There's a tangent line. Here's another one. All of these tangent lines that I've drawn in here, you should start to notice that because they're tangent, that's representing the derivative. Tangent slope is automatically what you get from the derivative. So I'm going to take this same exact picture and kind of redraw it, but only use the tangent lines this time. The original tangent line was actually a 1. And then it went to 0. And then it went to -1. And then back to 0. And then back to +1 again. So if you notice, that is the same values that your actual slopes had on the preceding part. If I connect these dots, you're going to get something that resembles a cosine graph instead. If we wanted to, this thing would keep on going on and on and on forever. And so actually what you're seeing this time is that the original function of y equals the sine of x, the dy dx for it is the cosine of x. The instantaneous slope at each point can just be figured out by plugging in the cosine. On the next one, for the cosine, this graph, again, it has the same properties. All you have to do is look at what the instantaneous rate of change is at any particular point. You would start off at 0, but then you would have a -1, 0, +1, 0, And you would think, well, sine